Maximum likelihood estimation, or MLE, is a fundamental principle behind how generative AI models learn from data. In simple terms, MLE finds the model parameters that would make our observed training data most likely to occur. Think of it like being a detective working backward from evidence. If you find certain clues, what scenario would most likely have produced those clues? MLE helps our models answer this question mathematically. Let's understand this with our biased coin example. Imagine flipping a coin 10 times and getting heads, heads, tails, heads, 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 heads. That's 8 heads and 2 tails. If the coin were fair, with the probability of heads equal to 0.5, the likelihood of this exact sequence would be 0.5 raised to the power of 10, which equals about 0.001, 0.1%. But if the coin were biased with a probability of heads equal to 0.8, the likelihood becomes 0.8 raised to power 8 multiplied by 0.2 raised to power 2, which equals about 0.017, 1.7%. The maximum likelihood estimate is therefore 0.8, as it makes our observed data 17 times more likely than assuming a fair coin. MLE simply picks the parameter value that maximizes the probability of seeing our actual data. In generative AI, this same principle applies, but with far more complex models and parameters. For a language model trained on the sentence, "the cat sat on the mat," MLE would assign a probability of 1 to mat following "the cat sat on the" and 0 to other possibilities like dog. With more training examples, these probabilities would become more nuanced. The visualization shows how the model distribution purple line gradually approaches the true data distribution dashed line as training progresses. This process is at the heart of how generative AI systems learn to produce realistic outputs. Understanding MLE helps explain why generative models sometimes struggle with rare events or outliers. They're optimized to capture the most likely patterns in the training data, potentially missing unusual but valid cases. Modern approaches often combine MLE with regularization techniques to address these limitations while still leveraging its powerful ability to capture the most common patterns in data. Loss functions in machine learning have a fascinating connection to probability theory that isn't immediately obvious. When we use common loss functions like mean squared error, MSE, we are actually performing maximum likelihood estimation under specific probability assumptions. Mean squared error is one of the most widely used loss functions in machine learning. It calculates the average of the squared differences between predicted and actual values. Mathematically, we are finding the average of prediction minus actual squared. This penalizes large errors more heavily than small ones due to the squaring operation. What many practitioners don't realize is that minimizing MSE is mathematically equivalent to maximizing the likelihood of the data under a Gaussian normal noise assumption. Here's the key insight. When we use MSE, we are implicitly assuming that errors in our data follow a bell-shaped Gaussian distribution. Our visualization shows data points scattered around a true relationship line, with the Gaussian noise represented by the bell curve. This means we expect most errors to be small, near zero, with decreasing probability for larger errors and positive and negative errors being equally likely. The math works out because the negative log likelihood of a Gaussian distribution is proportional to the squared difference between the observed and predicted values. Therefore, minimizing MSE is exactly the same as maximizing the likelihood under a Gaussian assumption. This connection explains why MSE works well for many real-world problems, because measurement errors in many natural phenomena approximately follow a Gaussian distribution. When we're predicting housing prices, for instance, and we use MSE, we're implicitly assuming that prediction errors, like predicting $210,000 when the actual price is $200,000, follow a normal distribution. Understanding this connection gives us valuable insight into when MSE is appropriate to use. If we believe errors in our specific problem might follow a different distribution, perhaps with more outliers than a Gaussian would suggest, then other loss functions might be more appropriate. This insight also helps explain the mathematical foundations of why many standard machine learning approaches work as well as they do. Different loss functions correspond to different assumptions about the probability distribution of errors in our data. While mean squared error assumes Gaussian distributed errors, mean absolute error, MAE, makes a notably different assumption that has important practical implications. Mean absolute error calculates the average of the absolute differences between predicted and actual values. Mathematically, we are finding the average of the absolute value of prediction minus actual. Unlike MSE, which squares errors, Massachusetts E treats all error magnitudes linearly without disproportionately penalizing larger errors. What's fascinating is that minimizing MAE is mathematically equivalent to maximizing the likelihood under a Laplace distribution assumption. The Laplace distribution visualized in our diagram has a sharper peak and heavier tails than the Gaussian distribution. This means it expects most errors to be very close to zero, the sharp peak, but it also considers occasional large errors more likely than a Gaussian would, the heavy tails. Our visualization shows how the Laplace distribution differs from the Gaussian. Instead of a smooth bell curve, it has a pointed peak and edges that taper more gradually. This shape reflects its greater tolerance for occasional outliers while still expecting most predictions to be very accurate. This connection explains why MA is often more robust to outliers in data. If you are building a model where occasional large errors are expected or where outliers are present, Massachusetts E might be a better choice than MSE. For example, in a stock price prediction model, occasional large market movements, outliers, are a natural part of the data, making MAE potentially more appropriate than MSE. In practical terms, models trained with MAE tend to be less affected by extreme values in the training data. While an MSE trained model might significantly alter its parameters to reduce a few large errors, potentially at the expense of smaller errors, an MAE trained model will balance its attention more evenly across all data points. Understanding loss functions as probability assumptions helps us make more informed choices about which loss function is most appropriate for our specific problem domain based on the error distribution we expect to encounter rather than just using the most common loss function by default. Understanding loss functions as maximum likelihood estimation provides profound insights into how generative AI systems actually learn and create new content. This connection is central to how these models develop their remarkable generative capabilities. When we train generative models, we are essentially finding the model parameters that make our observed training data most likely to have been generated by the model. Each type of generative model implements this principle in its own way, but all are founded on the same core idea. Cross-entropy loss, commonly used in language models and many other generative systems, corresponds to a categorical distribution assumption. When a language model predicts the next word in a sequence, it's providing a probability distribution across all possible words in its vocabulary. The cross-entropy loss measures how well these predicted probabilities match the actual words that appear in the training text. Minimizing this loss means maximizing the likelihood of generating the actual training sequences. In generative adversarial networks, GANs, the generator creates samples that aim to match the real data distribution so well that the discriminator can't tell them apart. The adversarial loss functions in GANs ultimately drive the generator to produce samples that maximize the likelihood of being classified as real data. Variational autoencoders, VAEs, explicitly optimize a likelihood function combined with a regularization term. The reconstruction component of their loss function represents the likelihood of generating the input data, while the KL divergence term regularizes the latent space to follow a standard normal distribution. Diffusion models, which have produced some of the most impressive recent image generation results, use noise prediction losses that correspond to maximizing the likelihood of the denoising process, matching the data distribution. The visualization shows how a generative model's distribution gradually improves during training to better match the true data distribution, the fundamental goal of all generative AI systems. This connection helps explain both the strengths and limitations of generative models. They excel at capturing common patterns in their training data because maximum likelihood estimation prioritizes the most frequently observed patterns. However, they may struggle with rare but valid examples that don't contribute as strongly to the likelihood function, which explains some of the ongoing challenges in ensuring diversity and coverage in generated outputs. Callback libeler divergence or KL divergence is a fundamental metric that measures how one probability distribution differs from another. This concept is essential for understanding and improving generative AI models. In simple terms, KL divergence measures the extra information needed to represent samples from one distribution using a code optimized for another distribution. The larger this value, the more different the distributions are from each other. Our visualization shows two distributions. The blue curve represents the true data distribution P, while the orange curve shows our model's approximation Q. The shaded area between them gives a visual sense of their difference. Areas where the curves differ more contribute more heavily to the overall KL divergence. The formula for KL divergence is the sum over all possible values of x, of P of x, multiplied by the logarithm of P of x divided by Q of x. This always yields a non-negative number that equals 0 only when the distributions are identical. KL divergence has three important properties. First, it's always non-negative. The divergence is 0 or positive. Second, it equals 0 only when the distributions are identical, when P equals Q. Third, it's asymmetric. The KL divergence from P to Q is generally not the same as from Q to P. This asymmetry is crucial in practice. When training generative models, we typically minimize the KL divergence from the real data distribution to our model distribution, not the other way around. KL divergence appears throughout generative AI, from the loss functions of variational autoencoders to evaluation metrics for generative models. It provides a principled way to measure and improve how well our models capture the true patterns in data. In image generation, KL divergence measures how well generated images match real ones statistically. Our visualization shows two cat distributions, real cats blue and AI generated cats orange. The pixel value histograms reveal subtle differences between distributions. When KL divergence is high, generated cats might have unrealistic features or missing details. As models improve, this divergence decreases. Generative models like VAEs explicitly minimize KL divergence during training, while diffusion models and GANs implicitly reduce it through their specialized loss functions. Direct sampling, the simplest approach where samples are drawn directly from the learned probability distribution. While straightforward, it only works well for certain distribution types. Markov chain Monte Carlo (MCMC) uses a random walk process that gradually converges to the target distribution. This method is particularly useful for complex, high-dimensional distributions, with Gibbs sampling being a common example. Importance sampling. Samples are drawn from an easier proposal distribution and then weighted appropriately to represent the target distribution. This technique enables sampling from otherwise intractable distributions. These sampling methods essentially translate the mathematical models learned by AI into actual generated content. Language models use top K sampling to select the next word by limiting choices to the K most probable options. For example, selecting model after the artificial intelligence from among the top 5 highest probability words. Diffusion models start with random noise and gradually denoise it step by step into a clear image. Used in DALI and stable diffusion to generate images from noise. Variational autoencoders, VAEs, sample points from a normal distribution in a latent space, then decode these points into new examples. This connects the mathematical representation to actual content. Bayesian principles provide a robust mathematical framework for understanding how AI systems can reason under uncertainty. At the heart of this framework is Bayes' theorem, which can be expressed in English as the probability of A given B equals the probability of B given A multiplied by the probability of A divided by the probability of B. Or more simply, posterior equals likelihood multiplied by prior divided by evidence. This theorem is fundamental to how modern generative AI models form and update their beliefs based on new information. The three components of Bayesian reasoning: 1. Prior beliefs, initial assumptions before seeing any evidence. In AI, these are the initial parameters or distributions. 2. Likelihood, how well the model explains the observed data. This measures the compatibility between data and our hypothesis. 3. Posterior beliefs, updated understanding after incorporating new evidence. This represents the refined model after learning. Applications in generative AI models. 1. Variational autoencoders, VAEs. VAEs apply Bayesian principles by prior, using a standard normal distribution in latent space as the initial assumption likelihood, employing the decoder network to determine how well latent variables explain the data. Posterior, learning an approximate posterior distribution via the encoder network. Example in action. When a VAE learns to generate faces, it initially assumes features follow a normal distribution prior. As it sees real faces, it updates its understanding of how features relate posterior. When generating new faces, it samples from this refined understanding. For instance, if a VAE sees many faces with glasses, the posterior distribution shifts to better represent the relationship between glasses and other facial features, making generated faces with glasses more realistic. 2. Language models. Modern language models incorporate Bayesian thinking through prior grammatical rules and general language patterns. Likelihood, patterns observed in training data. Posterior, updated understanding of language after training. Example in action, consider predicting the next word in the artificial intelligence. Initially, the model has a prior distribution over all possible next words. After seeing many examples where model follows similar contexts, the likelihood of model increases. The posterior combines this likelihood with the prior, making model a strong candidate for generation. This process works similarly for more complex text completion, where the model continually updates its posterior beliefs based on each new word it generates, creating coherent, contextually appropriate text. 3. Diffusion models. These cutting edge image generation models use Bayesian principles through prior, starting with pure noise, a known random distribution likelihood, the denoising process that gradually reveals structure. Posterior, the refined understanding of the image distribution. Example in action. When generating an image of a cat, a diffusion model starts with random noise. Prior, it then applies a series of denoising steps, each updating its beliefs about what a cat should look like posterior. Each step improves the image quality by applying learned patterns from training data, likelihood, gradually transforming noise into a recognizable cat image. The remarkable quality of modern text-to-image systems like DALL-E and Stable Diffusion stems from this Bayesian approach to iteratively refining visual information. Practical significance. The Bayesian foundation of generative AI enables several powerful capabilities. 1. Uncertainty quantification. Models can express confidence levels in their outputs, which is crucial for reliable decision making. 2. Incremental learning. New data can update model beliefs without complete retraining, similar to how humans continuously learn. Summary of key probability concepts in generative AI. This encapsulates everything we've covered so far about how generative AI works mathematically, from distribution types, uniform, Gaussian, multimodal, to probability relationships, joint, marginal, conditional, to critical techniques like maximum likelihood and KL divergence. We've explored the sampling methods, direct, MCMC importance that transform distributions into actual outputs, and Bayesian principles for updating beliefs with new evidence. Together, these fundamentals enable AI systems to learn patterns from data and generate novel, probabilistically coherent content.